Welcome back to CCAI321 Artificial Neural Networks, and we continue with our topic of Chapter 7. So today we'll look at a number of examples, and this is the first one. We have here 4 patterns that are to be classified into 2 classes. So we got this binary 4-dimensional pattern and this one over here. Both of these should both belong to class 1. The other 2 belong to class 2. So the blue field over here represents a 1. The white ones represent a minus 1. And the first question before us is, are these categories linearly separable? And seems that the answer is no. So, if they're not linearly separable, then how to move forward? So, what we basically want to do is let's give these 4 patterns some names. Let's call them P1, P2, P3, and P4. And P1 and P2, these 2 guys up here. P3, P4 are these 2 down here. And what we want to do is, if the neural network sees or encounters P1 or P2 as inputs, we want them to be on one side of some decision boundary, and if we encounter P3 and P4, we want them to be on the other side of that decision boundary. That's what it would mean for these patterns to be linearly separable. So if the input is P1 or P2, the value of WP plus B should be, say, greater than 0 for both P1 and P2. And if the input is P3 or P4, the value of WP plus B should be less than 0. So P1 and P2 can be represented, in addition to graphically, can also be represented, have to be represented now as vectors. So we have 1, 1, minus 1, minus 1. Let me just show you very quickly how we mean that. So 1, 1, minus 1, minus 1. So we're reading these top down from the left column to the right column. And we have minus 1, minus 1, plus 1, plus 1. We have minus 1, minus 1, plus 1, plus 1. So if I open up those equations that we saw, we get, sorry, let's jump back. So we get these 4 patterns if we read these images that way. So 1, 1, minus 1, minus 1 for P1, minus 1, minus 1, 1, 1 for P2, and for P3, 1, minus 1, 1, minus 1, and for P4, minus 1, plus 1, minus 1, plus 1. So let's plug these vectors, these input vectors, in here. So what we're saying is that W times P, and if W contains these 4 weights, then if you do that, if you take the dot product of these 2 vectors, you take the vector-vector product, you get this term over here. And this should be greater than 0 for P1. And it should also be greater than 0 for P2 then, because P1 and P2 both belong to the same classes. Let's take a look. So we use P2 for input now. I'm just writing this input as in its transposed form. So you open that up and you get this term over here. Now look closely. We have W11, W12 minus W13 minus W14 being greater than 0, and then we have the signs effectively reversed on each of the weights in the second equation. We have a minus, minus, plus, plus signs over here, And that should also be greater than 0. That's not possible. You cannot multiply this inequality that you have up there. You can't just multiply that. Both things cannot be true at the same time. If you multiply this inequality by -1, yes, you'll flip the signs on all of these four terms that you have on the left-hand side, but this greater than sign will also then flip to become a less than sign. So both these conditions cannot both be true at the same time. And guess what? The same is true for inputs P3. So I'm going to multiply that vector with the weight matrix, weight vector in this case. I get this equation over here. I do the same thing for P4. I get this equation. You can see that they both have less than 0. They both have less than signs, but the signs on the weights, on all the weights, are exactly the opposite. So again, both of these conditions cannot both be true at the same time. Which means, since both cannot be true at the same time, there's no linear. It's simply not possible to make these classes linearly separable. So let's take another approach, more manual approach. Okay. So I can decompose all of these four possible input vectors, these prototype vectors. I can decompose them like this into individual terms. And what I can see from there is that basically I want to have the neural network give as output class 1, or call it 1 if you want, if the first input is 1 and the second input is 1. So that's basically this situation over here. Or if the last two entries, or the last two inputs, are both 1. This one or this one. So I have an OR condition in between. So you can already see the use of the AND operation over here and the OR operation combining the two. And I can do something very similar for class 2. So if first and third input are 1, that's this situation. Or if the second and fourth together are 1, I want this neural network to classify this as the other class, class 2. There are no other input combinations, so that's really all we need. So we can design a classifier. We can design for a classifier for class 1, and if something is not class 1, it will just automatically be called or put into the other class, class 2. We already are familiar with how to make AND and OR gates, so the weights that you can use are not unique. This one, in this example, we use different weights from the ones we used in the previous examples we did. So for an AND operation over here, we're using 2 and 2 as the two weights, -1 for the bias value, and that will perform as an AND operation. For an OR operation, we can use 2 and 2 for the weights again, but use 1 as the bias value, and that will perform as an OR operation. And here are the inputs, different inputs, intermediate outputs, and outputs from the activation function. And you can see it works when, for the AND gate, only when both inputs are 1 is the output also 1. In all other cases, the output is minus 1, or what we're treating as the equivalent of 0. For the OR gate, as long as at least any one input is 1, the output will always be 1. The only case that both inputs are minus 1, the output is also minus 1. And if you want to put these gates together in the form of a whole network, this is what that'll be. This is the AND operation for class 1. I have another AND operation between P3 and P4. Also for class 1, if either of these sends us a 1, then the OR operation being performed in the second layer will output a 1. If it's not a 1, it'll be a minus 1, and that will mean, so the 1 will mean class 1. A minus 1 at the output will mean class 2. So this is a very simple example, building on using a lot of the building blocks that we're already familiar with from previously in this chapter. Let's move on to a more extensive example. This is still a binary classification problem, but as you can see over here, the prototypes over here with the black, represented by black dots, black markers on the XY plane, on the P1, P2 axis, in the P1, P2 plane. Those represent class 1. I'm sorry, the white circles represent class 1. The black circles represent class 2. Now it's again quite clear that it's not possible to draw a single line and separate class 1 prototypes from class 2 prototypes. So we have to use a multi-layer neural network. So the sum total of all the decision boundaries that we need drawn together look like this. Looks a little overwhelming, I know. So basically, if an input lies inside the box created by the 4 decision boundaries that you see on this side, so anywhere inside here, meaning to this side of this boundary, and to this side of this boundary, and to this side of this boundary. So anything inside this square that we have kind of drawn, any of those inputs will be considered class 2. And then kind of the same idea being used on the other side. So any input that is bounded by this box, any input bounded by this box, and any input bounded by this box. These will anything falling in any one of these 4 boxes that I've just drawn will be considered class 2. Everything else will be considered class 1. So basically belonging to the category of these white dots. I'm going to go through this example really quickly because we're performing operations we've performed many times before now, but we're just performing them more times. So I'm going to number these decision boundaries. So I'm calling them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So each number is for a specific decision boundary that you see over here. So 1 is for this one, 2 is for this one, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And so by now you should be very, very familiar with how you find the weights and biases for one specific decision boundary. We are going to do the same thing here now, not just for one decision boundary, but for all 11. So for the first one, I'm just going to walk you through this slowly. We pick 2 points. We picked over here 0.8 and 1.2, so somewhere over here, 0.8, 1.2, and then we pick another one at 1.8. I'm guessing 1.8.2, so I'm guessing that's somewhere over here. So we have these 2 points on decision boundary number 1. Using them, we come up with a vector between these 2 points, AB. We find an orthogonal vector, and that orthogonal vector happens to be W1, which is 1, 1. And this is what 0.11 means. It's a vector pointing in this direction. So this direction, this red arrow that you see drawn over here. Anything to that side will produce a positive number, a 1. We do the same thing for decision boundary 2. So for decision boundary 2, again, pick some 2 points on that boundary, get the vector, find an orthogonal matrix, and adjust the signs to make sure it's pointing in the right to the proper side. So in this case, to this side. And the weight matrix we find is 1 minus 1. If you draw 1 minus 1, that is 1 minus 1 this direction. So that's what you see drawn over here. So this is this decision boundary number 3. We do the same thing for decision boundary number 4. You get this vector in the end, minus 1, 1. So minus 1, 1, this direction, right? That's what we have over here. You get decision boundary, get the weight matrix for W5. That's this one. I'm just jumping over the individual steps of picking 2 points and all that. We've got W7 over here. All right, W5, W7. We then find the weight matrix for decision boundaries 6 and 8. 6 and 8. That leaves us with decision boundary 9. That's that over here. Decision boundary 10. That's the one over here. And decision boundary, 10 and 11. That's the one over here. So we have all weights for all decision boundaries together. We can put them into a single matrix, each column over here representing one decision boundary. So this is boundary 1, 2, 3, 4, 5, and so on. You can count them. This is 11. So after you get the weight matrix, what is the next step that we always do? What we need next is we need to find the corresponding 11 bias values. And to do that, what we do is we pick points on, we'll start with the first 4 decision boundaries, 1, 2, 3, and 4. We pick 4 points, 1 on each of them. So we pick this red one on decision boundary 1, this green one on decision boundary 2, this blue one, purple one, I guess, on decision boundary 3, and this yellow-green one on decision boundary 4. And we proceed the same way we did before. We use that equation with the weight matrix for the decision boundary with this point, with the coordinates of this point that we chose, and find the corresponding bias for decision boundary 1, that is bias B1. And in this case, we come up with the value minus 2. You do the same thing for decision boundary number 2, decision boundary number 3, and decision boundary number 4, and you get corresponding bias values for each of them. And we continue with the same for numbers, decision boundaries number 5, 6, 7, and 8. Again, picking points on each of those boundaries. And you do the same thing for number 9, 10, and 11. And when you're done, you end up with, you get the whole bias vector. So you have the weight matrix, you have the bias vector, you've got everything you need for the first layer. So if neurons, or basically if the decisions for decision boundaries 1, 2, 3, and 4 are all one, meaning, like I said previously, the input vector lies within this box created by boundaries 1, 2, 3, and 4, then the output should be 1. This represents this bounded box over here. But this was not the only bounded box that we drew, remember? So other options are, if neurons 5, 6, 9, and 11 all give us positive values at the output. If 5, 6, 9, and 11 are all 1, then another output should be 1. This would be a second output from the second layer. And so we'll add one output for the second layer of this neural network, in which we're performing these AND operations between outputs from the first layer. We're basically counting, we're basically checking if the input that is given to the neural network, if it lies within any one of these 4 boxes that we drew. So this is the first one, the second one. The third one is between boundaries 7, 8, 9, and 11. 7, 8, 9, and 11. So which one is that? That's this bounded box over here. And finally, if the decisions from neurons 5, 8, 9, and 10, the outputs from 5, 8, 9, and 10 from in the first layer are all 1. 5, 8, 9, and 10, meaning this bounded box over here, then that should also give us a 1 on a 4th output. Now, if an input falls within any one of these bounded boxes, then the final output, the class label, should be class 2. And that is something that we'll do in the third layer. So up in the second layer, we're performing AND operations between different boundaries, different decision boundaries, and that's represented here in these terms in the weight matrix of the second layer. So 1, 1, 1, 1. So each row over here represents one bounded box. So the first row is this bounded box. The second row was this bounded box. The third was 7, 8, 9. So this was the third bounded box, and this one over here I think was the 4th and last. I may be a little wrong on the order, but yeah. Which leaves us with bias, and as before, I'll just tell you what the bias vector will be to create a 4-input AND gate, and in this case it happens to be -3, -3, -3, and -3. For a single AND gate with 4 inputs. Finally, what we want to do is we want to OR in the third layer. We want to OR together the 4 outputs from layer number 2 And if any one of them is a 1, the output should be 1, and that should tell us that the class that the input belongs to is class 2. For all other cases, it'll mean class 1. And for that, for layer number 3, the weights will have to be, for an OR gate, for a 4-input OR gate, the weights have to be 1, 1, 1, and 1. The corresponding bias for a 4-input OR gate is 3. So I'm giving you this. We did not derive this over here. I'm just giving you this as for use as is. And if you put these 3 layers all together now, we have the decision boundaries implemented in layer number 1. We have the AND operations for each of the bounded box happening in layer number 2. And we get 4 outputs from here. So 11 outputs from the first layer, 4 outputs from the second layer, and then we're ORing them all together. If the input lies in any one of those 4 bounded boxes we created with the decision boundaries, then we need to OR these 4 inputs together, and that's what we get at the output. A 1 by 1, basically a single value that tells us if 1, the input belongs to class 2. If -1, the output belongs to class 1 or anything else. So I know that was a bit of a lengthy example. So there are a few short, kind of partial examples I'll show you next. So we have here a 2-layer network with given initial weights and biases. And the input target pair is 1 for the input. Output should also be a 1. And the way to proceed here is find the squared error, and the squared error is t minus a2, t minus a2. But this is, of course, this is the architecture of the neural network. So t minus and a is just equal to all of this. Quite complex, I know. So this is the relationship between input over here and output over here. Taking the difference with what the target output is, subtract the actual output from it, and take the square of it. That's the squared error. So, find the derivative of the error, of the squared error in this case. So take the derivative with respect to W1. Do that. And because the squared error 2e comes out here, then you take the partial derivative of all of this of this huge term with respect to W1, and you get this thing over here, again applying the chain rule. A1 can be found easily enough by putting P1 equal to 1 at the input. We have weights and biases. The output comes out to 0.8808. That is applied as input to the second layer, and the output from the second layer is minus 0.7616, which makes the error t minus a2 equal to 1.7616. Now that we have the error, we can plug that in to this term over here. The derivative of the squared error, so that's where this number over here comes from. Evaluate this whole thing, and you come up with 0.7398. That was still just forward propagation. And the next step is, of course, back propagation. We now need to adjust the values of weights and biases. First step, find sensitivity of the second layer. that. It's the error term over here, t minus a, that's just e. And you get a value for that. Based on that, find the sensitivity for the first layer using the sensitivity of the second layer. So that goes over here. Evaluate, and you get 0.7398. Partial derivative of error is 0.7398. Okay, another small example. Here we have a two-layer network, again given initial weights and biases. And now the input is -1, target is still 1, learning rate is set to 1. The forward propagation step, first we have compute n1, get 2, pass that through the activation function, and you get a1, the output of the first layer. Use that as input to the second layer, of course, and you compute the intermediate output n2. Over here, that is a1 right here being used, and you get the intermediate output n2 of the second layer. Give that as input to the activation function, and you get a2 comes out to -0.7279. And that lets us, since we have the target value, which is +1, we now have the output value. That lets us compute the error, which is 1.7297. Next step is performing backpropagation. For that, again, we begin by finding sensitivity of second layer. We have the error value, of course. Plug that in, get -1.6175. Use that as to compute the sensitivity of the second layer, of the first layer. So that's where this comes from. And you get 0.2285. Now it's time to use the R2D2 and C3PO equations to update the weights and biases. That's again straightforward. We have everything we need now. We have the learning rate is fixed. We have the old weights. We have the learning rate, which is fixed. We have the new sensitivities, and we have outputs from each layer. So it's a lot of math to do on a calculator, but easily enough done. And for the updating the bias values for both layers, that's slightly simpler than that, but done the same way. And for the last example, so this question asks you to derive the backpropagation algorithm. It doesn't actually mean derive the algorithm. Back when we should have done it, I explicitly said we're not deriving the algorithm or anything. But what's happening here is we basically we're given a neural network architecture, and we're basically being asked to write all the relevant equations in terms of the dimensions of this particular network. So N1 is, of course, this. A1 is common stuff. The return value from activation function F1 when given N1 as argument. So these are the basics that I think you should know by now. For a two-layer network, that means finding or updating the weight matrices. Do that. And this is basically the same equations that we have from before, only with these terms substituted with according to the specific dimensions of the problem that we're working on. So this is a two-layer network. So for the second layer, this is how you get the this is the sensitivity, derivative of n of the second layer with respect to all the w's, and this is the intermediate output for second layer. So this is basically the partial derivation that I showed you redone, but now assuming that we don't have m layers, we have a neural network with only two layers. So it's basically a simplified version of the equations, of the general equations that I showed you in that backpropagation info section. So remember, this was how we updated weights and biases for an M-layer neural network, which means in our case, when two-layer neural network, M can only be 1 or 2, which means the weights for second layer will be updated like this, and that's it. That is the end of chapter 7, and we'll move on to the next chapter in the next lecture.